All right, well, good afternoon, everybody. My name is Justice Calderon, and I'm a mechanical engineer.
My name is Connor. I'm a chemist.
Sarah Gould, I'm a biological engineer.
Gilbert, I'm an electrical engineer.
I'm Vincent, and I major in math and physics.
And our capstone project was on osmotic energy harvesting power plants.
As an initial assessment, we measured the value of our system using the Sustainable Development Goals, which was created by the United Nations to advance toward a healthier planet by the year 2030. Of 17, our project can address 6 of these, beginning with affordable and clean energy, because our system will be an alternative renewable energy source for areas that don't have a reliable and dependable renewable energy that's conventional on hand. These sites and energy plants that will be created will help to promote decent work and economic growth, and the system itself will promote and change and improve industry innovation and infrastructure, as well as sustainable cities and communities. And because the system will be closed loop and will not have any negative environmental impacts, it can be a responsible consumption and production. And finally, since it doesn't have any depletion on any of the other goals, it can be said that it helps to promote partnership for the goals.
So the first question that you're probably asking is, what exactly is osmotic energy harvesting? It's based on the concept of blue energy, which is just energy that is affected and based on osmotic processes, specifically energy created during the mixing of high and low salinity liquids. Salt water is an example of a high salinity liquid, and fresh water is a low salinity liquid. It's also based on the motion of ions through those liquids. It occurs all the time in nature, in things like your bloodstream, but recently it's become a subject of interest with regards to the energy that it generates during the mixing process. So there are a couple reasons why we're doing it. The first is as a potential alternative renewable energy source, because there are a lot of areas that don't have access to things like hydroelectric, geothermal, wind power, or solar power. So being able to introduce another alternative energy source to those areas would be extremely useful. This is a map of the United States showing you where in the country different sources or different renewable energy sources are more or less prevalent. The second reason is that it's a closed loop, like Sarah mentioned, which means two things. The first is that there's less maintenance that has to be worked on it, because there are a lot less moving parts that are going to be interacting with the local environment. And the second thing is that because it's a closed loop, there isn't going to be a risk of runoff or contamination to the area, dealing with things like salt water and high salinity liquids. That's entirely within the closed system, so it isn't going to leak and destroy the fresh water. It's not going to damage the environment. And then the third reason, which Justice will talk about in one slide, is it adds value through two things. The first is called cap mix, and the second is the heat engine.
So as Connor just mentioned, and here's basically a simple diagram of our power plant. As Connor just mentioned, we have something called cap mix in our system, which is short for capacitive mixing. It's a controlled process that will be in our osmotic energy cell, which Gilbert will talk about a little bit later. So kind of walking through how the process would work, we would place our osmotic energy cell in a freshwater source. We would have an intake for the freshwater here, take it through to a flash tank where we separate the fresh water from the salt water. We use the steam from the flash tank, send it through a steam turbine, which is common in geothermal power plants, and we can produce electricity right then and there. And then we take it through a condenser to put it back into liquid form, and then put it back into the source. And as you can see here, the salt water just comes out of the flash tank and keeps cycling back through our process.
Alright, so here's a diagram of the cell that we have. On the top, we have the two electrodes, which establishes an electrical gradient, and that's followed by the two membranes, which are selected for ammonium cation and carbonate anions. How that works is pretty much the salt solution goes in, or the ions get deposited onto the two electrodes, and then we put in the fresh water, which discharges the electrodes, and that produces the electrical power, which charges our storage cell. Now, this pretty much runs around constantly, just ideally constantly, and when the city requires more power and stuff, we will discharge our storage cell and send our power to the city. But if that's not enough to help the city, we'll just directly couple this to the city to give them power. Now, before we release the solution, we'll heat that slightly, and Connor will explain why in later slides. The electrode we chose will be graphite carbon because one, it's the most stable carbon form, it's very electrically conductive because of the electrons that's free to move in between. It's relatively light and it's pretty cheap. And you can see the cost of them on the board. And most importantly, it's a very common element. You can get it anywhere, so we can replace the electrode if we need to pretty easily, and we can get them pretty easily.
So for ion selective membrane, the dominant material is PVC. So we also use PVC for our device. However, PVC requires a plasticizer, usually some kind of organic liquid. The first reason is that plasticizers impart elasticity. Pure PVC breaks spontaneously. And the second reason is that plasticizers serve as solvents for ions. The best ratio of plasticizers to PVC is 2 to 1. If the ratio is too low, there will be high electrical resistivity. If the ratio is too high, PVC will be sticky and jelly-like. It will be unable to support the process. As you can see, we use different kinds of plasticizer for different kinds of ions. And an advantage of PVC is that it is cheap. The price is about $1,900 per ton. We calculate the power produced as a function of the concentration of salt water by the formula shown. And we find the maximum is reached when the fraction is 0.37. And the maximum power produced is about 40 megawatts.
All right, so it's been mentioned a couple times that we're going to be working with a salt solution. It's important to clarify this isn't like sodium chloride or any other like table salt, anything like that. Instead, the salt solution that we're going to be using is a combination of two gases, ammonia and carbon dioxide. And there's a couple reasons why we're doing that. First is that an ammonium carbonate cation anion solution is really commonly used in the literature when it comes to osmotic energy cells, indicating that A, it's relatively prevalent, and B, that it's relatively useful. The second reason, and this is what Gilbert was referencing earlier, is that as they're gases, if you heat up the solution while it's as it's moving, you can actually evaporate out the ammonium and carbon dioxide, meaning that there's no risk of the salt solution leaking out into the atmosphere. Instead, the ammonium carbon dioxide will be removed, and the fresh water can safely move out back into the stream. The third reason is that due to their low molecular weights, they form an extremely efficient salt solution, which means there's going to be good energy transfer to the fresh water, which makes them really useful in the cell.
So with our project, there's still some open-ended problems that would require further research and development. One of the primary things that we'd have to consider in our heat engine concept is the management of the thermal energy. So we were considering two different sources of our energy would be metal hydride heat exchangers. And the reason why that's relevant and it could be considered valuable is because it utilizes hydrogen. And in the United States and also globally, hydrogen is being utilized and the infrastructure is growing because PEM fuel cells are becoming a big thing in transportation and also in other industrial applications. Another thing that we could consider is biofuel for our thermal energy because it's an organic fuel. And in using that, we can essentially use mechanical devices that are already available to convert the chemical energy to thermal energy. We would require further materials development to just ensure that we're using optimal materials and their configuration are optimal for energy extraction. Energy storage devices such as batteries and steam turbine integration will also have to be studied, as well as the geological relevance as far as what areas need this sort of power source primarily. So with our project, we would like to start off with a prototype, like a laboratory scale prototype. It would probably be about the size of like a refrigerator. So this is just kind of like a cost analysis or a bill of materials. Purchasing the electrodes, the membranes, the heat exchanger flash tanks, the piping connections, the generators, and condensers in the control system. It can range from about $17,000 to $18,500. And what we would do is essentially set up our power plant system in a small laboratory scale and also model our own ecosystem to see how it would impact a simulated environment. So before we put it out into the field.
Now, in order for our idea to become a reality, we need to establish our partnerships and identify our revenue streams. So our capital investments, which include our prototype, will mainly be funded through small business grants and innovation technology awards. Some of the organizations that offer these awards and that might be interested in our new system will be the Department of Energy, the National Science Foundation, and the National Renewable Energy Laboratory. Our research and development partnerships will be with building laboratories who have the equipment available that we would need to borrow and use for testing and data acquisition. And our main revenue stream will simply be power utility companies who would buy and then resell our stored energy and the energy electricity produced by the steam turbine.
Questions?
What's the efficiency of this system?
The efficiency kind of depends, like that's stuff that would have to be tested because the different salts have to be tested at different concentrations. And the efficiency highly depends on what thermal process that we use, because some of that energy that we use to generate heat would probably be a parasitic loss from what we harvest. So it's kind of like, okay, how much energy are we putting back into the system instead of storing it away? What's up?
So I think you mentioned somewhere that carbon dioxide is produced in the system. So what are your plans for that? Or like, how is that going to be?
It's not that carbon dioxide is produced in the system, but the way that we're creating our salt solution is dissolving carbon dioxide gas into water. But and the same thing with ammonia. But before releasing into a stream, if you heat up the solution, you can remove it from the water. It's not that we're generating it; it's that that's already a part of the solution. We're just removing it.
So you can use that carbon dioxide for a later process.
Exactly. Okay. Yeah. So it can be just constantly restarted.
So that's like a part of the closed loop part that it stays in its own stream and it doesn't ever interact with the natural environment.
Yeah. Also, to give another part of the answer to your question, the efficiency of it also depends on the concentration of things like ammonia and carbon dioxide in the fresh water, because the greater the difference, the more energy is going to be generated during the transfer.
Yeah.
I don't know if you mentioned this. What amount of energy might you expect to get out of one of these, maybe refrigerator-sized units?
So we said 40 megawatts. Was that like per? So 40 megawatts for one of the salts.
40 megawatts
From your
On the
graph.
efficiency of it. That was with a 1 molar concentration of each, I think, right?
for
He's asking like the power production.
the power is the maximum is 40 megawatts.
It would probably have to be scaled down versus like depending on the size, but
The flow rate is 40 meter cube per second.
okay.
I guess just more as a clarification, what's actually going into the system to create the energy?
So what's going into the system, and I'm just going to go back to the diagram to show you. What's going in is fresh water. That's coming from outside of the system. It's mixing with the salt solution that's already there. And then it's going through steps 2, 3, and the 4B and A. And then after all of that, it's going to be leaving. So the only thing that's coming and going is fresh water. Everything else is completely closed.
So the actual where the electricity is coming from is So what happens is in this cell, and this is why we have valves here to control the process, is that you insert salt water first, and then you have the electrodes which suck salt to the sides of the cell. Then you pump out that water, put in fresh water, and then you put the salt in the new fresh water. So that process right there is what generates the electricity. It's like a weird physical phenomenon, but that's just how it works.
Yeah.
So yeah.
I mean, my thought was just, right, any sort of energy, you need a fuel going into it or some source. And so you're saying that the fresh water that you're putting in and then is leaving is the source of this energy?
Well, the salt water is essentially the source. That's our working fluid. The fresh water is required to help the process continue.
Okay, thank you.
Just out of curiosity, where in the diagram is the actual potential difference being created?
So what you have here is you have a steam turbine generator, which is your basic turbine generator that you would see anywhere else. This can produce electricity readily. Here we would be extracting the voltage from a capacitor. So you're an electrical engineer. So this is a supercapacitor. What we're going to be doing is charging the capacitor through the discharge process. And then once that discharge process has completed, we eject the water out, and then we close the circuit and send it to our cell. So it's going to be like a consistent like on-off switching where it's like charge, discharge. But that energy is going to be stored in a battery, essentially. Where this electricity is just mechanical to electricity.
So since this osmotic energy, this kind of system, you plan on to scale it up, right?
Yeah.
But the membrane that you selected is PVC, which is not necessarily eco-friendly. So is there like alternative materials that exhibit, the properties that you want, but also is like environmentally friendly and like a suitable cost?
I'm sure that there's definitely materials out there because they have things called microbial fuel cells, which use more organic polymers, I guess you could say. And that stuff could be studied to see what we can do with it, but there will be further like material science and engineering behind that to figure out what exactly is the optimal solution. As a test station, we would probably use it to kind of like concrete our concept, and then we can move forward from there.
How about the existing proven osmotic cell that now is proven that what do they use PVC for their membrane as well? Or do they use another material?
Use PVC.
Yeah.
What are you guys adding to the existing osmotic cell? I don't know if that's phrased right.
I think I know what you're saying. So, like currently, they have a process called desalination, and what companies or what factories are essentially doing is they're taking their wastewater, putting it through a filtration system, and then using the salt water and feeding that into one of these. But instead of putting it through a closed loop process, they're putting this mixed solution out into the environment. So it's essentially taking wastewater, cleaning it up, but you're still probably putting in like chemicals and compounds that should not be in the environment out into the environment. So using this sort of process will help with sustaining the environmental impact, if that makes sense.
And you get more energy out of it using the water vapor. So.
Well, yeah, it's kind of like using two processes at once. So this is something that's already existing, but putting our thing with it is our product.